In this video we will perform the chi-squared goodness of fit test, and we have 4 categories of 4 different genotypes, and we expect the numbers of observations in these categories to be in expected ratios of 9 to 3 to 3 to 1. But experimental observations give us 125 in the first category, capital A, capital B, 28 in the second, 39 in the third, and 8 in the fourth. And we wish to test whether these numbers, these frequencies of observations, could have occurred by chance in the expected ratios, or whether there is a difference between the observed ratios and those expected. The first step is to calculate the expected proportions as a fraction of 1 based on expected ratios. And to do that, we add up this number in the ratio column just by using the sum function, giving us a total of 16. But then for the first category, the proportion of 9 out of 16 is a simple ratio of just equal to 9 divided by 16. And we wish to use this same formula for each of these other calculations, but when we copy the formula down, we will refer to different ratio values, but we want the total value to remain as B8, so we need to lock the 8 value using a $sign. We can then copy it down, and these ratios are now converted to proportions, and the total of all these proportions will be 1. We now have to add the total number of observed values. So again, we use sum of all the values, giving a total of 200 observed events. We now have to calculate the expected numbers in each category, assuming that we observed a total of 200 events, but in these particular proportions. So for the first category, the expected number will be a proportion in C4 multiplied, i.e. a proportion of the total number 200 in D8. Again, we will put a $sign in front of the 8, giving us an expected number of 112.5 in the first category, as opposed to the observed number of 125. It is worth noting at this point that it is okay for the expected number to be a non-integer value, 112.5, because this is a theoretically calculated number, but any observed numbers must purely be integer values, i.e. exact numbers of observations. We will calculate the expected numbers for all the others just by copying the formula down. We now wish to use the chi-squared test to test whether these observed numbers are significantly different from the expected numbers. And to do that, we start off by just taking the simple difference is equal to the observed minus the expected, again for all of the data. And then we calculate the chi-squared contribution for each of these categories, which is just equal to the difference observed minus expected, which is in F4, but squared, which is up arrow 2, divided by the expected value, which is in E4, and we copy this calculation for all of the categories. So we have chi-squared contributions for each of these categories. The larger values show the largest deviation between observed and expected. The chi-squared value is the sum of all of these, which again is the simple Excel function, giving a chi-squared value for this calculation of 5.48. Clearly, a large difference between observed and expected will give a larger value of chi-squared. And we wish to test whether this value of chi-squared is larger than would be expected by pure chance. And for that we perform the hypothesis test, and we must define the significance of the test as 0.05. This is for a 95% confidence. The degrees of freedom for this test are the number of categories, which is 4 minus 1. So the number of degrees of freedom here are 3. And then we calculate the chi-squared critical value. And because we are performing a one-way test, testing whether the chi-squared value is larger than expected, we will choose the upper or right-hand probability part of this distribution, and we enter the probability, which is the significance probability in this case, and then the degrees of freedom, which are 3, giving us a chi-squared critical value of 7.81. But then, because our measured chi-squared statistic of 5.48 is less than the critical value, we will not reject the null hypothesis. There is not enough evidence to say that the observed distribution is significantly different from the expected ratio. We can also calculate this as a p-value, and we could use the chi-squared distribution function, chi-squared dist rt, in which we will have equals c chi-squared dist rt, and we have to put in the chi-squared value and then the number of degrees of freedom, enter, and we have a p-value of 0.140. And again, because this is greater than the significance value of 0.050, we do not reject the null hypothesis, giving us the same overall conclusion as before. We could also use the chi-squared test directly, equal to chi-squared test, in which we have to identify the actual range of values, which is the observed, and enter the expected range and enter, again giving a p-value of 0.140.